I'll just quickly introduce you again. Although I assume all the participants already know DJ, they were in this. You are already attended the lecture number 10 that was on deformation behind shock waves, and you had that probably at the time to go over the problems and work on it, and you might have some questions. With that, I'll hand over to DJ, and if anybody has questions, they can start asking their questions. If you don't have any question, then the instructor will start going through the solutions, and you can ask question while he's presenting the solution. So is anyone has any question on the problems that were posted, or in general any question on the lecture?
Good afternoon, everybody. I just have a question about the shockwave deformation in macro scale, and I'm thinking about the huge explosion in Beirut last Tuesday, and you see everybody see a huge blast wave in the air after the explosion, and my question is that blast wave is also the shock wave? And also we see many shattering window around the area, and my question also, what is the main mechanism of deformation in the window? Is that caused mostly because the difference in pressure or deviatory stresses? That is the mechanism, right? And that's my question, I think.
Yeah, that's a nice question because it illustrates some of the things we've been talking about. And I guess there's two parts of it. And let me summarize what I think, what I understand the question to be. So the first question is with regards to the video and the images that have come out from this explosion that just occurred. Whether that what you see, whether that's the shock wave or not, that sort of the, when the blast, there's a couple camera angles I think that you can see where you really see this dynamically moving blast coming right at the camera. And then the second part of the question is that all the damage that occurred, like for example, to all the windows and the glass, what was that caused by, and what was the nature of the wave, in relation to that damage? So the first question, so the blast generated a tremendous amount of pressure in a short amount of time. That's the actual explosion associated, with the source. That generates a tremendous pressure. The media that wave is transmitted through is the air. And so air is a fluid. And so there's no appreciable deviatoric stress. If there were any, it would just be because of the viscosity of air. And so we could essentially, if you go back to, undergraduate mechanics of fluids, we can think of the air as an inviscid fluid, which means there really is no shearing stress. There's just pressure. So it's just a pressure wave. And that pressure wave travels at the shock wave speed. So if we knew the equation of state of air and we could plot the shock Hugonio, then we could go through these techniques that we've been talking about, or that we talked about in the lecture, to figure out what the particle velocity and the shock velocity of the air would be. And so that's the answer to the first question, is that what you see, obviously we've got to look at an actual specific video, and I don't have one, but to be real precise, but what I saw in the videos I was looking at, that blast wave is a shock wave in the air. And so, you're deforming the air through volumetric compression because, and through conservation of momentum, that's transferring the pressure out radially from the source. So, but then what we have is all this damage. And so the specific question was the glass that's breaking. Well, once that wave hits the surface of a glass window, it's imposing that pressure state on the glass. And if you impose a tremendous, significant enough of a pressure on a glass window, you're going to break it. Now, the mechanism of fracture within the glass is not due to a purely hydrostatic state, but what happened is that by applying this pressure to the surface of the glass, you could think of just applying a pressure to a plate or, like a shell, right? And if you apply a pressure to a shell, you're going to generate a three-dimensional state of stress within the shell, and that's going to include tension because of like plate or shell bending, right? So if you apply a pressure to the window, you're going to create tension on the opposite side, and that's going to just, at these levels of pressure, that'll just fracture the glass, and then the glass is carried downstream in the moving fluid flow of the pressure wave that's continuing on. So I hope that answers that question, and it does seem like it's relevant to the discussion on shock waves. If there aren't other questions about the lecture on shock waves, I think I'll just go through the solutions to the problems, and then maybe you'll have more specific questions about those solutions. So one of the slides I presented before I got to setting up the actual homework problems is this slide where we're looking at results in terms of the free surface velocity, which, remember, the free surface velocity, that is the measurement of the wave structure itself within the media as the wave structure arrives at a free surface where you can, where you can actually observe or measure the behavior. So it's sort of the effect of the structure of the wave as it breaks out of the specimen. And then we talked about these characteristics where you have an elastic precursor. And so this plot on the left is showing the rise, the initial wave that arrives as the elastic precursor, and then that plateau is associated with the Hugonio elastic limit. So that marks the transition from purely elastic deformation to accommodating some of that deformation through plastic slip mechanisms, and then the arrival of the secondary wave. And then I pointed out that for these curves shown on the plot in the middle, what has happened is for increasing specimen thickness, which is the number that's written next to each curve, so a thickness of 0.125 millimeters, we see a relatively narrow separation between the elastic precursor and the secondary wave. And that makes sense that that separation would increase as we increase the thickness from the red curve to the black curve. We're not, but the experimentalists increase the thickness of the specimen. And so because the thickness of the specimen was increased, the travel distance of this wave was increased. And if we have an elastic precursor that's moving at a faster velocity than the main shock wave, then we'll see the separation between the arrival of the elastic precursor and the final shock wave. We'll see that separation grow. Okay, but then all of this was to set up the homework problem, which is that we observe that the precursor magnitude is also decaying as the wave transmits into the material. And one of the main points of the lecture was to connect that aspect of the shock wave structure to the deformation mechanisms. And so in this case, in the case of the homework problems, that's connected through the dislocation velocity behavior and the availability of mobile dislocation. This plot on the right, finally, is measurements from this experimental paper of Zaretsky and Cannell on tantalum. It's a plot of the stress, the axial stress within the material at that point of transition at the elastic precursor. So that's the stress associated with the Hugonio-elastic limit. And that's plotted on the y-axis versus the propagation distance of the shock wave on the x-axis. Okay, so this is all just setting the stage for the homework problem. So it worked through, so we briefly went over these expressions which provide an analytical or semi-analytical, because ultimately you had to evaluate this numerically, scheme to solve the problem. Or maybe, I mean, actually, I suppose you could have put everything together and come up with an analytical solution, and that would be fun also. So the expression in the top is showing a differential equation for the spatial variation of the stress at the Hugonio-elastic limit as a function of the plastic strain rate right at that incipient point of going from elastic behavior to initiating plastic slip right at the shock front of the elastic precursor wave. And so what we have is a differential equation in terms of the evolution of that stress with run distance, x, in terms of some parameters. So the G is the shear modulus, and that is provided over here for tantalum as 71.3 gigapascal. Then the plastic strain rate, which we're going to talk more about subsequently, divided by the longitudinal wave speed. So the longitudinal wave speed is an acoustic limit at zero pressure. So that's an ambient, if you will, acoustic limit. And that means that if we impart a longitudinal wave, just a tiny perturbation, just a small deformation wave into the material, and it's a longitudinal wave, it's going to travel about 4 millimeters in every microsecond. But that's not the same as the shock wave. It just depends, because the shock wave, it depends on the final Hugonio state in the Rayleigh line, the loading line to get there. But this C subscript L is the rate of propagation of an acoustic perturbation for a longitudinal wave. Likewise, C sub S is the same thing, but for a shear wave. So for pure shear wave as opposed to a longitudinal wave, which includes, bulk deformation or a volumetric deformation and a deviatoric deformation. Okay, but we got to find somehow to relate, we need to close this differential equation, so to speak, in the parlance of differential equations. So we have this rate term, but we need to connect that back to something in the solution in terms of the stress. So the way we do that is that we recall the Orowan relation, which is that our gamma dot is equal to the dislocation density multiplied by the magnitude of the Berger's vector multiplied by the dislocation velocity. And then I said, okay, well, let's use a specific model for the dislocation velocity. Can you guys see my, can you see my mouse? In fact, wait a minute, I should go into, is that better? Probably that's a lot better to see. Anybody want to weigh in? Can you see the screen better now that I've?
That's better.
Yeah. And then can you see my pointer, the mouse?
Yeah. Yes.
Okay, good. So I just provided a dislocation velocity model, and this is actually one that comes from the paper that we're borrowing these relations from, which is an early analysis from Taylor in 1965 on this problem. So the dislocation velocity is related to that shear wave speed that I mentioned, which is about a propagation rate of about 2 millimeters every microsecond. But that's scaled or factored by an exponential and the free parameter or the model parameter is tau star. And the tau is the actual applied shearing stress. So what we're saying is that a dislocation is going to be driven by the shear stress, tau. That shear stress, as we increase it, is going to increase the velocity that the dislocation moves at. And if you could visualize what this curve is, which is actually the first thing I asked you to do, you would see that it's going to limit out at this shear wave speed. So that means the dislocation will, under the highest stresses, will move at a rate of about 2 millimeters every microsecond through our material. And then I said there's some other closure or important relationships you would need to solve the problem. One is that the relation between this axial stress sigma, which is what our differential equation is expressed in terms of, and the shearing stress that's moving the dislocation, we can approximate that by the ratio of the shear wave speed to the longitudinal wave speed squared. So that's the coefficient that's relating the axial stress, which includes pressure, of course, to the shearing stress that's driving the dislocation motion. And then the other relationship we need is that the plastic strain rate is just 2/3 of the shearing slip rate for this particular problem. Okay, so then, I had several problems specific problems or questions that I put out, and I said, first, just plot that dislocation velocity versus the stress for several values of the tau star parameter, just to get a feel for how the parameter and the shear stress affect the dislocation velocity. And so the first solution, that's pretty easy. I gave you the expression, and I'm just asking you to plot that for different values of tau star, and I gave a range from 0.5 GPa to 5 GPa. So now I'm plotting the dislocation velocity normalized by the shear wave speed. So I divided V by CS, and of course, if I do that, all I'm plotting is the exponential of the negative of the parameter divided by the state of shear stress. And so what we see is that there's an asymptote of the dislocation velocity at very high stresses. We're not even, we're just getting up towards 90% of that asymptote. But the dislocation velocity will asymptote to the shear wave velocity, C subscript S, at sufficiently high stresses. But in the meantime, what we see is a relatively rapid rate of increase in the dislocation velocity at some lower stress magnitude, and then the plateau out at higher stresses. So you could sort of think of this as two regimes of behavior. And then as we increase the tau star parameter, we're flattening that curve, and so we're essentially increasing the stress at which we're increasing the stress required to attain a certain dislocation velocity and to ultimately attain the maximal state of the dislocation velocity. I mean, of course, an asymptote, we're never going to get exactly that maximum velocity, but you can imagine, this is an asymptote, and we're just delaying our approach to that asymptote by increasing the tau star parameter. So tau star acts as a drag strength, so to speak, which is defining, the resistance to the stress resistance to dislocation velocity for this particular model. So that's the solution to the first part of the problem. I'm not going to actually show you code for how to make a plot. I think everybody could write a Python script or MATLAB or whatever you use to plot that function. But that's the main thing is the observation of this behavior. Okay, so then the second question is, well, how would you describe the rate sensitivity in relation to that plot? Well, I didn't actually see the lecture, so I'm not sure how the rate sensitivity and plasticity was described to you. But the sort of a traditional approach or model for that is to invert the relationship to write out the stress, the shearing stress, as a function of the plastic strain rate, and then solve for this rate sensitivity exponent m, which is the derivative of the log of the stress divided by the log of the strain rate. And those are normalized because that's the only way really that a logarithm makes sense, right? So that tau 0 is the normalization stress and epsilon dot 0 is the normalization strain rate. And those are physically motivated based on our particular model. So I'll describe that, we'll walk through those steps. So we have the plastic strain rate, epsilon dot p, is equal to 2/3 times the dislocation density times the Berger's vector magnitude times the dislocation velocity, which is given by this expression because that's our dislocation velocity model. Now, when we collect all those things, what we see is out front a convenient term which is which provides or defines a reference strain rate, epsilon dot naught or epsilon dot 0. So this reference strain rate is 2/3 times the mobile dislocation density times the magnitude of unit slip, which is the Berger's vector magnitude B, times, did you guys hear me okay? Did I lose my connection?
Still good.
Okay. I noticed my mouse kind of froze, so I thought, oh, maybe my Wi-Fi connection went, but okay. So multiplied by the shear wave speed. If you multiply all these things together, you'll find that that provides some upper limit of what plastic strain rate we can accommodate within the material given that particular value of the mobile dislocation density. So that's what epsilon dot naught represents. That's an upper limit for the plastic strain rate we can accommodate according to this model. Now, we can quickly recognize that there's a convenient normalizing stress, tau 0, which is just directly this parameter, tau star. So if I make those substitutions, I end up with a plastic strain rate is equal to upper bound reference strain rate multiplied by the exponential of the negative tau 0 over tau, where again, tau is our driving stress, the shear stress, and epsilon dot p is the plastic strain rate in the material. And so just for the sake of convenience, I'm going to define a variable z, which is the logarithm of the plastic strain rate divided by the reference strain rate. So that I just defined z as that. And so based on that definition and this model, we see that that's just equal to minus tau 0 over tau. Okay, but I want to get the log of the stress over the normalizing stress, tau sub 0, and then take the log of it. So if I do that, based on just the algebra here of this in this definition, I'm taking the log of minus 1 over z, which is equal to the negative log of negative, which you can do this however you want, but that was a useful identity for me in terms of performing the derivative that I need. So the final step is to take the derivative then of this term, so the derivative of the natural log of tau over tau 0 with respect to my z variable, because z is the natural log of the plastic strain rate over the reference strain rate. So when I perform that operation, I get that the result for m is just the negative of 1 over z. So if I plug the definition of z back in and plug back in my definition of the reference strain rate, I get this solution. For my rate sensitivity exponent is the negative of the inverse of the log of the plastic strain rate over 2/3 times the mobile dislocation density times Berger's vector magnitude and the shear wave speed. So let's look at some limits. If we take the plastic strain rate to 0, then our rate sensitivity goes to 0, which means that at a strain rate of 0, we are basically rate independent. We don't have rate sensitivity. Whereas if we take our strain rate to this maximum upper bound strain rate of 2/3 the mobile dislocation density times B times the shear wave speed, then then the rate sensitivity goes to infinity, which means as we approach the upper bound for the rate or for the strain rate at which we can accommodate plastic deformation according to this model and at a given value of dislocation, mobile dislocation density, our rate sensitivity goes, grows without bounds. So the material model becomes incredibly rate sensitive at the limiting values of strain rate. Now, if I plot the stress versus the plastic strain rate, which is what I've done in the lower right, but this is in log-log space, which is useful because then I'm looking at the slope of this curve is M, right? If I plot log of stress versus log of strain rate, and then, then the slope of that is my M, essentially, or proportional to M. So we see that these limiting conditions, that as we decrease the strain rate, we're decreasing the rate sensitivity. As we increase the strain rate up to some limiting value, then the slope grows without bound up to infinity. And we also observe, so I'm plotting this now for 3 different values of the mobile dislocation density. So if we increase the availability of mobile dislocations, we decrease the stress at all strain rates. Okay, so that's an important point. As we increase the available mobile dislocation density at any strain rate, we will decrease the stress. So that means that at a given strain rate, we're decreasing the strength of the material or the resistance to plastic deformation at a given strain rate by increasing the availability of mobile dislocation. But we also increase the upper limit for the rate at which we can accommodate deformation through plasticity. So we're also, by increasing the mobile dislocation density, essentially that means we're increasing this upper bound epsilon dot 0, which is the maximum rate we could accommodate an imposed deformation via plastic slip. Okay, so that's the second problem. Are there any questions so far on the solutions to 1 and 2 before we get into the precursor decay problem? Okay. Then I'll just run through the answer or the outcome of, or we'll describe the problem again, and then I'll go through the outcome before I look at, how we actually solved it. So again, I'm throwing the figure on the screen for the experimental measurements from Zaretsky and Cannell on elastic precursor decay in tantalum as you increase the propagation distance from, in this case, from 1/10 of a millimeter to 1 millimeter. We see a drop in that HEL stress from just under 10 GPa down to just over 1 GPa or below, I guess, depending on the temperature. So I picked reasonable values. One of the things I noticed in the solution that I didn't provide you is you need to know the HEL magnitude at 0 propagation distance in order to apply the solution scheme from Taylor. Because of this figure, I just took the liberty of picking a value of 10 for my solution. If you picked a different value, that's great. And if we did not know one, there would be some additional solution techniques we would use to estimate what that magnitude would be for a given shock condition, for a given shock loading. But without having specified that, I just picked a value of 10. So we say 10 GPa at a propagation distance of 0, and then I solve the differential equation, which I'll go into more details in a minute. I'll open up the Python script where I solved that. But what I want to do is look at the solution first and how it depends upon these two different parameters. So what we see is that the rate of decay of the axial stress at the Hugonio-elastic limit decreases more rapidly as we increase the availability of mobile dislocations. And so what that's telling us is that the more dislocations we have available to accommodate the deformation through plastic slip, the more rapidly our axial stress at the HEL will decay to a stabilized wave. On the other hand, at a fixed dislocation density, and I fixed the dislocation density here at 10 to the 8th per square centimeter, if we increase the value of that drag stress parameter, tau 0, then we decrease the rate of that decay. And so that's telling us that there's a relationship both between the mobile dislocation density and the drag stress associated with viscoplastic slip in defining the viscous behavior of how that elastic precursor wave is dissipated or decays with position. So that is the outcome, the answer, but I want to show a little bit more about how I arrived at that solution. So to do that, I'm just going to share, if I can, if I'm able to, my text editor where I developed the solution in Python.
Got it. Looks like you might have muted yourself, DJ.
Thank you for pointing that out. I guess when I changed the window that I'm sharing, it muted me. Can you see my text editor?
Yes.
Okay, great. So in this region here, I'm just defining the parameter values. So nothing exciting there. And this is all Python. You could do very similar in MATLAB, and you could probably work out a solution analytically. I didn't do that. I just evaluated it numerically. So within this while loop is the main solution strategy, which is I started a value at a position of x equals 0. So remember, this is a differential equation of stress within x. So x is our independent variable. That's the position. And the dependent variable is stress. And we're solving for that, how the stress varies with position. So I start with a value of that initial value, as I mentioned, of 10 GPa for the stress at the stress in the HEL at that initial position, x equals 0. And then I'm just going to loop through and advance by some value delta dx and advance the solution by dx using a forward Euler explicit finite difference approach. So very simple and direct. And then I just take very small steps in dx to ensure that I get a reasonably accurate and stable solution. So I've chopped my length of a half of a centimeter. So that would be like, the specimen thickness, if you will, a half a centimeter. I chopped that up into 1,000 chunks. So my dx is 1,000th of that half of a centimeter. And then I compute, so I'm just looping over, I'm looping over each delta x to advance the solution from the current position of x to the next position 1 dx unit to the right of that. So this closure relationship tau gives me the shear stress in terms of the axial stress, sigma. And again, that's just the ratio between the shear wave speed and the longitudinal wave speed squared. Then I compute the dislocation velocity according to that dislocation velocity model, which we've plotted and looked at a fair amount. And then I compute the derivative or the slope, you know, d sigma dx, which I listed here as just ds dx, which is minus 4/3 times the shear modulus normalized by the longitudinal wave speed multiplied by the mobile dislocation density times the Berger's vector magnitude times dislocation velocity. So what you'll see that I did is I just substituted a few expressions all into one. Essentially, we had a -2 times shear modulus divided by C sub L multiplied by plastic strain rate. The plastic strain rate is equal to 2/3 the shearing slip rate, gamma dot, and gamma dot is equal to the mobile dislocation density times Berger's vector magnitude times dislocation velocity. All those relations, you know, were in the slides. And so I just substituted those all into one expression and evaluated to get the slope or the rate of change of stress with respect to position. And then I store the current answer. So this is just, you know, this is just sort of a style thing of, you know, within Python, but I'm just storing my value of x, stress, and slope before I advance the solution to the right. So, so this is just, you know, storing the answer away so we can plot it when we're done. Then in line 44, I advance the solution. So I just say, yeah, the stress at 1 dx to the right of the value I just stored away is equal to the stress where I'm at plus ds, the slope, times dx. And this plus equals is just, you know, that's just a syntax thing in Python or in C++ or C or whatever, right? Hopefully that's familiar enough. And likewise, then I advance my position 1 unit to the right. So I add dx to my x to advance my x. So I've just advanced the solution here. And then I say, oh, if in advancing the solution, my x is now past L, past the end of my specimen, then I'm done. So I say this loop condition is false. Then when I come back up to the beginning of this loop, I'm not going to do it. So that'll be the end of that. And then I file away that whole stored solution into some results that I'm putting together. So then this outer loop is just kind of is just trying out the same thing, but for different values of the mobile dislocation density. So that's the solution strategy. Then the rest of this is just the details of making a plot, and that's not anything that we need to look at. So really, the solution scheme I used, right, is just to integrate the differential equation numerically using a forward Euler approach. So not anything too exotic or difficult. There's plenty of other approaches, and in fact, I think you might be able to analytically solve that particular differential equation, but I did not do that. Are there any questions with on the problems or on the solution strategy?